We present BitBio, visual odometry at 300 frames per second, using binary features from the focal plane. Why do we want a fast frame rate? The two main benefits of operating at a high frame rate for visual odometry are the reduction in motion blur and the small frame-to-frame motion. Both of these properties make the pose estimation problem simpler. For example, reduced motion blur makes the feature detection more reliable, and reduced interframe motion allows pose optimization to converge faster. However, most of the visual odometry systems operate at around 30 to 80 frames per second. Therefore, they suffer from both motion blur and large interframe motion when the camera motion is violent. Let's look at a typical sparse visual odometry algorithm. The camera transfers the images to the CPU, where the features are extracted, matched, and then optimized for pose estimation and mapping. We notice that the image intensity information is discarded after the feature extraction. This is a redundancy, as we have wasted time and energy transferring all the pixel information only to extract the features. Transferring and processing images are expensive, which prevent the visual odometry system from operating at a much higher frame rate. Instead, we might imagine a pipeline like this, where the computation of the features are pushed all the way up to the sensing device. This way, the only data transferred is the features, reducing the data bandwidth and also the computation on the CPU. One sensor which enables this is called Focal Plane Sensor Processor. In particular, we use SCAMP5, which is a prototype device developed by the University of Manchester. SCAMP5 is a massively parallel SIMD device. Each of the pixels on the device contains a photodiode and its own processing element. The processing element is able to perform analog computation such as addition, subtraction, and division by 2. Since the computation occurs in the analog domain, each operation adds some noise. Each of the processing elements come with its own set of registers. There are 6 analog registers and 13 digital bit registers. The processing element can communicate with its north, east, west, south neighbors by exchanging their register values. Here's an example of what SCAMP5 can do. On the left, we have the low intensity image captured by the device. On the focal plane, the image is processed into binary edges using the Sobel filters and thresholding, and into corners using fast algorithm. The image on the left is only for visualization purpose, and if this is not transferred, we can compute and transfer both edges and the corners at over 300 fps. Notice that the corners are flashing, appearing and disappearing between frames. This is caused by the analog nature of the computation, where the error builds up per instruction. The noisy corners are too unreliable, hence unsuitable for visual odometry. Later, we'll show how we can solve this problem. Here is a demonstration of BitBio, motion estimation and mapping using SCAMP5. BitBio operates at 300 fps in real time. Only the binary edges and the corner information is used in the system. As demonstrated, BitBio can operate even when the camera motion is violent. By operating at 300 fps, BitBio has low latency. The physical camera motion and the estimated motion matches even under fast motion. BitBio supports multiple keyframe insertion, enabling the system to keep expanding the map. This allows exploration of unseen scenes. BitBio is capable of initializing under fast motion. The video captured by the webcam suffers significantly from motion blur and exposure, where the features captured by the SCAMP5 does not. Our system uses a standard sparse visual odometry pipeline. In fact, the majority of our system shares common structure with other typical systems. The highlighted region indicate where BitBio differs from other systems. We perform corner and edge detection on the SCAMP5, which is transferred to the CPU. To overcome the noisy corners, we compute a small 44-bit descriptor for each of the corner using the edge image. Using the corners and the descriptors, it is matched for pose optimization and mapping. One of the interesting parts of our pipeline is our unique feature matching. As we have no intensity information, we cannot use descriptors such as orb, brief, or brisk. While the interframe motion is small, the noisy nature of the analog computation prohibits us from using a simple technique such as closest neighbor matching. Instead, we use a small 44-bit descriptor which is computed from the binary edge image. Around a corner of interest, we look at a 7x7 patch of the binary edge image. 3 links are created where each cell stores the corresponding binary value. To provide rotation invariance to our descriptor, we compute the orientation of the patch. Each of the links are shifted accordingly to align them. The ring is converted into a single vector of bits, which can be efficiently matched using Hamming distance. While the 44-bit descriptor is short, they are sufficiently expressive as our feature matching problem is simplified, since we are operating at such high frame rate. For the evaluation, due to the nature of the device, we could not use any standard benchmark for visual odometry. Therefore, we have evaluated our system with a custom dataset with ground truth measurement from Beacon system. Here we demonstrate that our system is able to track all 6 degrees of freedom pose accurately. The solid line is the estimate from BitBio, and the dotted line is the ground truth obtained by the Beacon system. We have compared our system against OrbSlam. Since it is not possible to operate SCAMP5 at a high frame rate while transferring all the pixel values, we have attached a webcam on the device to record the video. The red region indicates the cases where OrbSlam failed. As you can see, the webcam suffers significantly from the motion blur, which our system is able to accurately track as we operate at much higher frame rate. Similar to other work which can perform 4 degrees of freedom visual odometry on the SCAMP5, our system is able to track rapid rotation changes. Here we have shaken the device rapidly. This resulted in around 5 shakes per second. As we can see, our system is able to track accurately the rotation in all 3 axes. We have computed the absolute trajectory error for the different sequences used in the evaluation. We report the total trajectory length, the root mean square error, and the median error. We have performed the runtime evaluation of our system. For the top left figure, timing is measured offline over 10 iterations. The system is able to perform motion estimation in 1.1 millisecond on a standard laptop, which translates to a frame rate of over 900 FPS. On the bottom left, we provide a breakdown of how much time was spent per frame when operating the system live. This includes the idle time, where the system is waiting for the new feature from the SCAMP 5. The median is 3.33 milliseconds, which is 300 FPS. This indicates that the bottleneck of the system is a frame rate of the SCAMP 5, which is limited to 300 FPS when detecting both corners and edges. The figure on the right is a summary of the frame rate at which the different component of our system operates at. To summarize, BitBio is the first 6 degrees of freedom visual odometry system which utilizes the SCAMP 5 FBSB. The system is able to track motion at 300 FPS in real time with high accuracy even under challenging conditions. The overall pipeline of BitBio is simple and is lightweight as it takes advantage of the small interframe motion. Thank you for your attention.